Welcome to lecture 6. So in the first unit, crystallography, so we are going to see about the crystal defects, or you can say it as crystal imperfections. So as you know, the crystals consist of the regular arrangement of atoms. It's arranged in a periodic fashion. Okay, so if there is any misalignment of atoms, then it is said to be defect. Okay, so it is of different types. So let us see one by one in this lecture. So first of all, the classification of crystal defects. So based on the dimensionality of the defect, it can be classified into 4 different types. One is point defect, then line defect, surface defect, and volume defects. Now first let us see the different types of point defects. First one is vacancy, impurity, Frankel defect, and Schottky defect. In line defects, you have 2 different types, that is dislocation and disclination. And in the case of surface defects, you have grain boundary, twin boundary, and stacking fault. So here we are going to see about grain boundary and stacking fault in detail. And the final one is volume defects. It is classified into twins, precipitate, voids or cracks, porosity, and inclusions. So this has happened as a whole in a crystal. If the defects happen, then it is called as volume defect. Right. So let us start from the point defect. So here, these are the point defects of crystal. So first one is vacancy. If there is a missing of an atom, as you know, it is a regular pattern of arrangement of atom. If there is a missing of atom, then it is called as vacancy. So here an atom is missing, so it is called as vacancy. And interstitial impurity. Interstitial impurity means some foreign atoms are included interstitially. So here already it is arranged in a regular fashion. It is occupying in between that. Okay, so not replacing anything, but it is interstitially occupying the position. So that is why it is called as interstitial impurity. And then self-interstitial impurity, which means the same atoms, not a foreign atom, the same atom can included interstitially without replacing anything, and that is called as self-interstitial impurity. And the next one is substitution impurity. So substitution impurity means an atom is substituted by another foreign atom. Okay, so completely replacing one atom and the foreign atom occupying that particular place, and that is called as substitution impurity. Right? And two more defects are in point defects, that is Schottky defect and Frankel defect. So here this one explain about the Frankel defect. I'll explain this too. First, Schottky defect. So this Schottky defect is nothing but missing of equal pair of anions and cations. They are called as Schottky defect. And Frankel defect, the occupation of cation in the interstitial position is called as Frankel defect. So here equal number of cations and anions. Okay, so missing of equal number of cations and anions, and in this case industrial occupancy of cations. Okay, so these things already have studied in your lower class itself, Schottky and Frankel defects, right? So that's all about the point defect. So it is a one-dimensional defect, so just a point, there will be a defect in the one point, right? Next, line defects or line imperfection, otherwise called as one-dimensional defect. Okay, so here there is a defect along a line of atoms. So because of that, there is some slip or dislocations takes place. That is called as line imperfections. Let us see what are the imperfections due to this line defect. So here, as we have seen, it is of dislocation and also disclination. So here we are going to discuss only about the dislocations. In the line defect, it is of two different types. One is edge dislocation, another one is screw dislocation. So first one is, it explains about the line defect. So there is nothing but the edge dislocation. So here you see in figure A, you have a perfect crystal without any defect, and here you can see the defect because off-filled atoms are there along this line, but this particular region it is not filled. Okay, so because of the inclusion of this particular atom, the edges of this edge and this edge, both these edges got dislocated. Okay, and this is called as edge dislocation. Here it may be of two different types. In likewise the inverted T or in the T shape, English letter T shape. If it is upside down, then it is of this T shape. Okay, so this is what it is said to be edge dislocation. So because of this dislocation, there may be an enhancement of property in that particular material. So it leads to very good ductility and malleability. So ductility means making it into thread. Malleability means you can make it into sheets. So these things can happen. So normally these crystal defects, all these crystal defects are not harmful, because these crystal defects may enhance the property of the crystals also. So it is a desirable effect in some cases. And screw dislocation. So let us see what is the screw dislocation. Here again about this the same dislocation, edge dislocation. It is of three-dimensional form. You can see again here. Here you can see this is inverted T type and T shape also there, right? It also represents the same edge dislocation. Yes. So here is the diagram. So this represents the screw dislocation. You can see the slip of this layer of atom downwards. So here this particular region, up to this region it is fixed, and remaining it is moving just downwards. So just like the screw, the top surface is slipped down. It is similar to the thread of the screw. Okay, so that's why it is called a screw dislocation, and this line, dislocated line, is called as this is dislocation line. So it is happened in one part of the crystal and the relative remaining at rest. So only the dislocation happens here. So other regions remains at rest. Okay. Now the two-dimensional imperfection, there is surface imperfection. So here it is of different types: grain boundaries, tilt boundaries, twin boundaries, and stacking faults. So we are going to see about these grain boundaries and stacking faults. What is the grain boundary? So normally, single crystals means it is made up of a single crystal, and it has a perfect orientation. It will grow along only one direction. It has a certain boundary, not more than one boundary. Okay, so that is single crystal. If it is a polycrystal, then it may have more than one boundary. Likewise, the boundaries will be there. Okay. So, for example, if I draw this a cubical crystal, single crystal, it will grow along this particular direction. If it is polycrystal, then you have a different orientation. The growth of crystal in different directions are possible. So at this region, if you have a cross-sectional view, you have different boundaries likewise. Okay. So because of these grain boundaries, it will cause some defect onto the crystal. So that's why it is called as grain boundary. Here you see. Okay. So in this, in every grain, the atoms are in a particular direction. But when there is a grain boundary, it will be oriented in a different direction. But the atoms in that particular grain is same. So this defect takes place generally during the solidification, when it is in liquid state and finally it is converted to solid after the reactions and all. So at that time you can observe this. Particularly you can observe in the polycrystals and also in the nanocrystals also. If you make it into pellets, at the top surface region you can observe these kind of grains. And next one is twin boundaries. So here it is the mirror reflection arrangement of the other side. Okay, so here you can see here is the defective region, this is the defective region, this is the defective region, the parallel. So you have a set of atoms here and another set of atoms in this region. So this is 1 and this is 2, and this is a mirror image of this set of atoms in 1. So 2 is the mirror image of this set of atoms in 1. Okay. So that's why it is called as twin boundary. That is because of the change in atoms in this particular region. So that's why it is having this mirror image like this. So it will happen because of some strains happen in that crystal. And stacking fault. So what is stacking fault? So we have already studied different kind of crystal lattice structure. like SC, BCC, then FCC, HCP. Okay, so these four things already we have discussed in detail. If you consider hexagonal closed pack structure, it has a hexagon at the bottom, and in between you have three individual atoms, and again a hexagonal layer at the top. So you can consider this as A, and it is again repeated at the top, so again A. In between it is considered as B. So this is one unit cell, and followed by another unit cell at the top, again B, again A. It will go on like this. So arrangement, the stacking will be like this: A B A B A B, likewise. So this is the case of HCP. So for the HCP stacking, it will go on like this: A B A B A B. Okay. So if there is a fault, for example, instead of A B A B A B, if there is A B again followed by B, then it is a stacking fault. Okay, so this is a fault in that hexagonal closed pack structure. In the case of FCC structure, you have a different arrangement of atom that is given by ABC, 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 etc. So here, in this case, you have a different orientation. There is a change, that is A, B, C, B, C, A, and if there is a change, so that is called as the defect. So these are the stacking faults. Okay, for these particular structures, there is a stacking arrangement of atoms, so that should follow throughout, otherwise it will be called as stacking fault. And the last one is volume imperfection. So volume imperfection, that is happened as a hole in on a crystal. Okay, so it is visible nakedly to you, or even very smaller in size also. So it affected that crystal as a whole. So if there is a foreign particle inclusions inside, even if it have a value of 0.20 nanometer, and they are also called as volume imperfection. So it may affect a certain region of atoms. Then here, if there is a crack, then it is called as volume imperfection. So here you can see this is a crack occurred on the crystal, so it comes under this volume imperfection. If there is a large space, then that is also comes under this volume imperfection. Large vacancy or void space, so that's also comes under this volume imperfection. So that means a cluster of atoms, if it is missing, then it is comes under volume imperfection. Okay, so that's all about the crystal defects or crystal imperfection. So thanks for hearing. Thank you.